Hi everyone, this is video 3.2.1. We're going to continue talking about solubility here. So while soluble salts, and those dissociate 100% into ions, insoluble salts also dissociate a little bit. So we've been calling them insoluble and saying they don't dissociate at all. It's not exactly true. They do dissociate a small amount, and today we're going to figure out exactly how much they dissociate and how to figure that out. The maximum amount an insoluble salt dissociates is called its solubility, and is usually expressed in grams salt over 100 grams of water, or in molarity. More likely you see it like this, the moles of salt over liters of solution. And this is called the molar solubility, so this is important. This is the molar solubility, and that's the number of moles of salt that can dissolve in 1 liter of solution. Okay, so the equilibrium constant for the dissociation of an insoluble salt is called the solubility product, or KSP. So we have another K here, and it's related to the molar concentration of our products in this case. So here we have some salt, some insoluble salt, AX, and that's a solid, and that's in equilibrium with its 2 ions that it dissociates into, A plus and X minus. And so our KSP would be equal to the concentration of A plus times the concentration of X minus. And that's just the amount of ions that came off of this solid. So let's learn how to do this by looking at an example. So example 1, the molar solubility of silver sulfate at 25 degrees Celsius is 2.29 times 10 to the negative 2 molar. We're going to find its KSP. So we need to find this part, the KSP. And we're given the molar solubility here. And so this is how many moles of our silver sulfate can dissolve in 1 liter of water, 1 liter of our solution. So we can do our ICE table again, so initial change in equilibrium. And here, the solids, again, don't count. So you can go ahead and cross off the solids box. And we only are worried here about our ions in aqueous solution. So at the very beginning, initially, we don't have any silver ions. We don't have any sulfate ions. And then our change here, we're going to gain both of these. So these are both going to be plus. So plus 2, carry the 2 down. And I'm going to use the letter S for solubility when we're doing KSP. Here, I just have a 1. And then plus S. So I don't write the 1, you just write plus S. So overall your change here at equilibrium is 2S and S. So writing this as an equation, our KSP is equal to the concentration of our silver ions, Ag plus, squared, and that's squared because we have this 2 here. Our 2 is our coefficient, times the concentration of the sulfate ions, SO4, 2 minus, and then there's nothing there. That's just to the first power because the coefficient is also 1. Now substituting in our generic S's instead of the chemicals here, we get KSP equals 2S, so we have our 2S squared, so the 2S instead of Ag squared, carrying that down, times SO4, which is now just going to be S. So this is just going to be times S. And there's no exponent here. Okay, combining like terms, our KSP equals 4S cubed. Make sure you carry this 2, so 2 squared is 4. And we have this 2 plus 1 is 3, so that's 4S cubed. That's our KSP. So now we can go ahead and plug in a number for S, and we can figure out what our KSP is. So moving our work over here, KSP equals 4. Well, what is S? S is our molar solubility, and in fact we're given our molar solubility right up here. So this is your S, 2.29 times 10 to the negative 2 molar, and that's going to be all cubed. We're just carrying that here. So this is going to be S. Plugging this into your calculator, you should get KSP equals 4.80 times 10 to the negative 5. That is your KSP. That's how you would solve that kind of a problem. So that's numerically what that looks like. And then now let's go ahead and look conceptually at what this means. So what does this reaction mixture look like when 0.010 moles of silver sulfate is in a 1 liter solution? Well, we know we can dissolve this much silver sulfate in a 1 liter solution. So this means here Let's just go ahead and write down what this means. So this means only 0.029 moles can dissolve in 1 liter of solution. So let's compare that with what we're putting here. So here we're saying that we are going to put 0.010 moles of silver sulfate in a 1 liter solution. Well, we can dissolve up to this much, 0.029, and we're only going to put 0.010, so we're putting a lot less than can dissolve. So that means that since this amount is less than the molar solubility up here, all of it's going to dissolve. All of this 0.01, and then some can still dissolve, but all this is going to dissolve. So since the concentration of our silver sulfate is less than S, all of the salt will dissolve. What does this reaction mixture look like when 0.040 moles of silver sulfate's in that solution? Well, we saw up here that, again, looking at this, we can have this much dissolve. So that means that only 0.029 moles of this 0.04 moles is going to dissolve, and the rest is going to be left over as a precipitate. So now, since the amount we're adding, since the concentration of silver sulfate that we want to add is greater than S, 2.29 times 10 to the negative 2 moles, and that's the solubility right here, that's this number here, will dissolve. While the leftovers, so you're going to take your 0.04, subtract this number, and you should get 1.71 times 10 to the negative 2 moles. So while 1.71 times 10 to the negative 2 moles, which is excess, will precipitate out. And that's because we're adding more salt than the solution can handle at this point. Okay, let's look at another example, example 2. In this case, we're given the KSP, which is what we wanted to find last time. And we're going to calculate the solubility. We're going to calculate S. Here, like what does that S equal to? Okay, so we know that the solid gets crossed out. So that's your start. I'd like you guys to go ahead and now pause the video and see if you can fill in this ice table and then come back. Just fill in the ice table and come back. Okay, hopefully you had 0 to start with. Here we just have plus S. Here plus 2S. And then this is just going to be S and 2S. Now that you filled in the ice table and checked that that's correct, I'd like you to please write the KSP expression. So that's going to be the expression KSP equals something something. And I want you to go get all the way down into S's, get as far as you can to figure out what S is. So basically you're going to solve for S and then come back. Okay, so let's start by writing in the ions here. So our KSP is equal to the concentration of our mercury, 2 plus, times our chloride, so Cl minus, squared, because we have 2 of those, squared. So KSP equals S, carrying this in, times 2S squared. And we're starting to see a pattern here, right? Whenever you have that 2, you also tend to have that 2 here. So that might be important for you to remember later. So just notice that pattern. Combining like terms, KSP equals 4S cubed. We're given our KSP, so I can just plug in KSP here and solve for S. So here's our KSP at 25 degrees Celsius, so 1.1 times 10 to the negative 18 equals 4S cubed. And then plugging this into your calculator, you should get 6.5 times 10 to the negative 7 molar. That's equal to S. So that's the molar solubility. That's how many moles of our mercury chloride salt can dissolve in 1 liter of solution. So what does that mean? So we're going to calculate the solubility for both of these, so for mercury and for chloride. It's because they don't dissociate in the same ratio. So for every 1 mercury, you're going to have 2 chloride here. So the concentration, or the solubility, of mercury, 2 plus, is just going to be equal to S, because that was just S here. So we already solved for that. 6.5 times 10 to the negative 7 molar. That's its solubility. Chloride's going to be different because 2 of these dissociate for every 1 chloride. So really, this is going to be 2S. So the concentration of Cl minus is equal to 2S. So plugging that in, 2 times 6.5 times 10 to the negative 7. And you should get 1.3 times 10 to the negative 6 molar. So that's its molar solubility. So here's the solubility here for mercury, and there it is for chloride. Okay, go ahead and flip the paper over. We're going to look at one more thing. So example 3, we're going to rank the following salts in order of increasing solubility. We can't just use KSP alone to rank these in order of solubility because we need the molar solubility. We need S, and this is KSP. So S is what we just found in the last problem. So in general, KSP is going to tell you about how much that it's going to break up, the extent of the reaction. However, since they don't all break up in the same ratio, we can't use KSP alone to predict the solubilities. So in general, KSP tells you the extent of reaction. However, since not all salts break up in the same ratio, we can't use KSP to predict solubilities. Oops, predict solubility. Okay, so here we would have to use those ice tables for every single one, unless we can recognize a shortcut. So remember how I told you before to notice that when we had, let's go back. When we had like a 2 here, we ended up having a 2 here. So that's an interesting trend that we're going to exploit for our shortcut. So what we're going to do is we're going to quickly solve for S. So here's our shortcut. And we're going to call it our shortcut. Okay, so the first one, cobalt 3 hydroxide. So that means cobalt 3 plus and your hydroxide is OH minus, so you're going to have three hydroxides and 1 cobalt. So CO, OH, 3. So the cobalt, there's just one of those, so that's just going to be S. And OH3, there are 3 of them, so you're going to have 3 S, and that's going to end up being cubed, because remember, those numbers are going to match. So when you combine like terms here, we're going to combine all these like terms, you should get 27s to the 4th. So 3 cubed is 27, 3 plus 1 is 4, so 27s to the 4th. And that's going to be equal to its KSP. So here's its KSP, 2.5 times 10 to the negative 43 equals 2.5 times 10 to the negative 43. Plugging this into your calculator, you should end up getting S is equal to 9.8 times 10 to the negative 12 molar. Okay, so that's just bypassing the ice table. Now, if you don't like this method, if you don't like this shortcut, you can certainly use the ice table for every one to get to this point. And then you're just going to solve for S, just like we did in the last problem. But this is a shortcut way. I will accept either way on your tests. Okay, so at this point, I'd like you to pause the video, and I would like you to first just write the formula for lead-2-phosphate, then come back and check it, and then I'll let you go again. So just write the lead-2-phosphate and come back and check. Okay, so for lead-2-phosphate, you should have gotten PB3, and then phosphate is PO4, 2. So that should be your equation for lead 2-phosphate. Now at this point, go ahead and pause the video again, and I'd like you to get all the way to the end and calculate S. Okay, you have 3 leads here, and so that's going to translate to 3s cubed. You have 2 phosphates, so that's going to translate to 2s squared. And combining like terms here, you get 108 s to the 5th power, so 2 squared times 3 cubed, and that's going to give you 108. 3 plus 2 is 5, equals the KSP, 1.0 times 10 to the negative 54th. Plugging all that in, you get your S equal to 6.2 times 10 to the negative 12 molar. Okay, tin 2 sulfide, go ahead and pause the video and get all the way to the end to S. Okay, here we go. So tin 2 sulfide, tin 2, that means tin 2 plus. Sulfide is S2 minus, so SNS really is just your formula here. So you're just going to have S times S, that's just going to be S squared, equals the KSP, which is given up here, 1.0 times 10 to the negative 26. Plugging all that into your calculator, you get S is equal to 1.0 times 10 to the negative 13 molar. Okay, so now we have all our S's, our molar solubility. Remember, this is how many moles are going to be able to dissolve in 1 liter of water, in 1 liter of our solution here. So here you have the most moles, so 9.8 times 10 to the negative 12 is the biggest number here. This is the smallest number. So this is the most soluble. And so our cobalt hydroxide is the most soluble, and our tin 2 sulfide is the least soluble. Alright, that is the end of video 3.2.1.